Hi, so I'm Himanshu Verma. I'm a postdoctoral fellow, recently joined the group of UNN at LSE, and I'm in the working group survey, simulation, and pipeline validation. So today I'm going to talk about uh, some of the work that I have been doing in the last 2-3 months. Um, it's about lens flux analysis of gravitational microlensing events and how they the likelihood of measuring such lens flux with the Roman Space Telescope. Yeah, so this is my quick plan. I'll be talking about a very quick motivation about why do we want that, lens flux measurement, and a quick review of analytic estimate of the lens flux, which Ben Anderson Gaudi 2007 paper gives us, and then potential improvements that we try to do over that, those relations, including the proper motion and the error analysis using the color dependent centroid shift. And we'll see that what will be the detectability of the lens flux with the Roman and some further improvements. So we know that light curve gives us the duration of the event, which is basically the light crossing time over the Einstein angle. And if we want to measure the mass of the lens, then we require some other information as well because of the degeneracy of the lens mass parameter. And if we know the proper motion, then we can invert the Einstein. We can invert the relation and get the Einstein angle. And out of parallax or lens flux, if we have one of them, then we can break the degeneracy and constrain the amount of lens. It turns out that if we can detect lens in an image, we can actually measure the proper motion and lens flux simultaneously. So for many of the events, many of the planetary events, we know that we'll have a finite source size effect, and which can allow us to measure the proper motion. So that will be another handle. So ultimately, this is going to give us the mass measurement of the host star, and which is a level 1 requirement of Roman. So just to give you the idea, so what we can do is after the event happened, much later, we know that there is a relative proper motion between the lens and the source. And if we look at an image much later, we know that there will be an elongation of the PSF because of the presence of the two sources. So what Ben Anderson Gaudi they did is they assumed that we can really model the two sources with the double Gaussian, and in principle, what we can do is we can take the image and fit the model and get the optimized parameters, which gives you the lens flux fraction and the angular separation of the source and the lens. And if you know the time duration between which you have taken the image, that can give you the proper motion. Right. So this is like numerical MCMC way of doing it. But then, is there a quick estimate, analytic estimate, with which we can get the idea about the lens flux? With what uncertainty we can measure it? So there are observables that we can construct out of images. One is if you have these double sources, it's really one is the lens, another one is the background source. In that case, we can calculate centroid. We can calculate because of the separation of the two sources. There is a spread in the PSF, and if there is a difference in the lens flux fraction between the source and the lens, then there will be a skewness as well. So using these observables, in principle, we can kind of constrain the characteristics of the lenses. So the idea is following. If you assume that the PSFs are double Gaussian, the centroid will depend on what is the x naught. which is the center of the source. X naught, Y naught gives you the center of the source. And because of the presence of a lens at a distance of delta X, delta Y, the average position of the PSF will change. Similarly, the spread will depend on what is the angular separation of the source with respect to the lens and what is the lens flux fraction and skewness as well. Now we know that if we have observed like total number of photons from the image, we know with what accuracy these observables we can calculate, and we can relate these two and invert the relation in order to get what will be the lens flux, what will be the uncertainty with which lens flux can be measured, and the angular separation, and hence the proper motion. So if you invert this, you get uncertainty in the lens flux. As if you assume that okay, angular separation is measured using finite source size effect, then what will be the uncertainty in the lens flux fraction? So this expression is widely known to quickly kind of get the idea about what will be the uncertainty in the lens flux. So what we did is we included the uncertainty in the angular separation that will come from finite source, and the full expression becomes like this. So there are other terms which are like the higher order compared to this. But there is this last term which depends on how accurate you get the angular separation from the finite source effect. And in order to just compare like how important that extra term is, so I have just plotted here assuming that the angular separation is measured with 10% accuracy. And we can see that if the angular separation is very small, then it matches with the band 079 Anderson paper expression, which is really the first term. But if the angular separation increases, the 10% accuracy in the angular separation measurement, it actually worsens the lens flux measurement. Another observable that Van Anderson paper kind of proposed is using color-dependent centroid shift. So, so you can, if the color of the lens in two different bands is different, in that case, if you kind of if you look at the lens and the source system in two different bands, you can actually find out this centroid shift, and which will depend on how what is the color contrast of the lens flux and what is the separation between the lens and the source. So this is another observable along with these spread observable. So what we did is we calculated again using the what is best can be measured with with the average value and as well as the spread uncertainty, and we inverted that relation using the Jacobian analysis, and we get the with what accuracy one can measure the flux and the angular separation of the lens and the source, and hence the proper motion. So just to give you an idea what those expressions are, so you can see, so the solid lines shows what Van Anderson paper gives us, and the dashed line are the uncertainty which we can get from the color dependent centroid shift. So the first row is for the one of the band, which I have just used the white band of the Roman, and the second row is the Z band, and the last row is the fractional uncertainty in the proper motion. So we can see that in the white band, the color dependent centroid shift, that method will not be better than that, better than the just using the spread variable. However, if the color contrast is large, then it can be significant. But one of the benefit of color dependent centroid shift would be that it will give you the proper motion measurement at the same time. So what we did is we took the catalog which was generated by the Farzana, Matthew and et al. Where 43 seconds is the exposure time, cadence is 15 minutes, color cadence is 6 hours, that means Z, and sorry, the season is 6, and the planet mass is 0.1 Earth mass. And in that case, we can compare what will be the fractional events and how they will be distributed over the uncertainty in the W band, Z band, and the proper motion fractional uncertainty. And we can see that, and for the finite source, we have just assumed right now 10% accuracy would be for all of the events. And for some of the events, we can see like color-dependent centroid shift can give you a better accuracy compared to the finite source, 10% accuracy. So these are just preliminary results, and we want to kind of compare these analytic estimates with the MCMC, which can capture the effect of the gridding in the images, of course, and also the image boundary that Jay Anderson was also talking about. And of course, the blending will be another big issue. And we want to characterize these different methods with which we can actually calculate the lens flux fraction in our catalog, which we just have preliminary results on. So yeah, that's all from my side. There are questions.
That's great. So the relation you display, was it for only one image? I'm wondering, because Roman gonna take 40,000 images, so you increase a lot the statistics typically. So can you propagate that to more image, your relation?
Yeah, so I have included actually these 6 seasons. I mean, the exposure time I have taken, we integrated over a season. So the uncertainty ratio that you see over here, that is for that would be obtained within one single season. So whatever will be the number of images that will be required.
Yeah, so I was wondering, in some of your expressions, it seems to be sort of a higher order power law. But have you compared it to like doing fits to the images? Because as the separation gets larger and larger, at some point, adding more terms to the Taylor series doesn't convert that quickly, and so, and in particular, the skewness term, I think there's a higher order terms that are become pretty important quickly. So, have you compared any of this to just doing the fit between?
Yeah, so that comparison is still remains. So that is something which we want to do. Here we just added this extra term so that we understand if there is an uncertainty in the proper motion itself, can be combined with this in order to kind of understand how important it would be compared to like without using it. But we have to still compare it with the simulation, like what will be the applicability of these expressions. But for color dependent centroid shift, it's the leading order term that we got. So